Hello and welcome to the first in the series of geometrical and physical optics lectures. My name is Mo Hasanovic. I'm an assistant professor and department chair of Electronics Engineering Technology Department at Indian River State College. And this series is supported by LASER-TEC, which is a national center for lasers and fiber optics education located in Fort Pierce, Florida. As the title of this series indicates, we are going to be exploring the fundamentals of two important subfields of photonics, one being geometrical optics and another being physical optics. In the first portion of this series, titled Geometrical Optics, we are going to be applying the concepts of geometry to analyze the direction of the propagation of the light through different media. And then in the second portion, we are going to be analyzing different phenomena that are related to the wave behavior of light. After finishing this first lecture, you will be able to distinguish between the light rays and light waves. We are going to be spending a significant portion of this lecture explaining what the light rays and light waves are. We are also going to state the law of reflection and show with appropriate drawings how it applies to the light rays at plane and spherical surfaces. This, in a sense, is going to be a review of the material we covered in the video series in Introduction of Photonics. We are also going to analyze the Snell's law of refraction, which is going to be the law that quantifies another important phenomenon related to the light behavior, and that's refraction. So we are going to show a few appropriate drawings, and through those drawings we are going to explain how to apply the Snell's law of refraction to the light rays at either a plane or spherical surfaces. And finally, we are going to define index of refraction as an important parameter that's used in some of the phenomena that we are covering here. We're going to give typical values for index of refraction of materials such as glass, water, and air, which would be the most used types of materials in the photonics experiments. As already mentioned, geometrical optics represents a part of photonics, a subfield of photonics that analyzes the light behavior by using the light rays and the concepts of geometry. By applying the skills that you're going to acquire through geometrical optics, you will be able to better understand the basics of light reflection and light refraction, and then also how to apply those two basic laws of geometrical optics onto the optical elements and components such as mirrors, prisms, lenses, and fibers. In this, as well as in subsequent lectures, we're going to be looking at some of these optical components and we'll be analyzing how the light propagates through these components. Let's first define a light ray. Light ray is an imaginary line that's directed along the path of the light energy propagation. In other words, if you have a light source that produces the light is going to propagate along the straight lines. You can very clearly see those light rays if you're using a laser or a kind of more focused type of a light source. In the case of LED or incandescent bulb, those light rays are propagating in all possible directions, so it's not easy to see the light rays. But for now, remember that in order to apply the concepts of geometrical optics, we are defining a term called the light ray that represents the path along the light propagates from a specific light source. So think of a light ray as a thin pencil of light, very much like a narrow, well-defined laser beam. Now, in addition to the light rays, we are also going to introduce a concept of a wavefronts. Wavefronts represents a series of adjacent points that connect identical positions above or below the normal surface of the reference plane. So you can establish the analogy between the wave in the water or ocean wave. You have a crest of the wave, and if you connect all those points along the same crest, you're basically creating the wavefront. So geometrically, a light ray or propagation of light is perpendicular to the series of successive wavefronts, and you can see that in these pictures, right? So here on the bottom left-hand side, you can see the wavefronts that are in a circular shape. So all these points that are on the crest of the same wave, if connected, represent a wavefront. And then obviously the light or water here propagates in the outward direction from this quasi source of a wave. So the propagation of the water in the case of a water wave, or propagation of a light in the case of a light wave, is perpendicular to each of these different wavefronts. That can be much clearly seen in this picture on the bottom middle. So you can see the arrows here that represents the propagation of the light wave or light rays. And then you also have these circles that represent the wave fronts on the crest of the same wave. So if you connect again the points along the same crest of a wave, you create the wavefront. So very important relationship to be established between a light ray and a wavefront. Light rays are the directions that are perpendicular to the wavefronts, and light rays are basically representing the direction of the propagation of the light wave. You can see here on the right hand side also a lens. We are going to be using the concept of light waves and light rays in the case of a prism and mirrors and other components such as lenses as well, to analyze how the light propagates to a lens or other optical component. So you can see here the light rays, how they are changing the direction as they are passing through the optical lens. And then you can also see here as a dotted lines the wavefronts. You can see that in front of the lens the wavefronts were of planar nature, meaning they are represented by the straight lines, while behind the lens, after the light passes through the lens, you can see more of a circular curved shape of the wavefronts. So we are talking about so-called circular wavefronts. So we are using a simple geometrical idea of a simple light ray to illustrate the propagation, reflection, and refraction of light in a clear, uncomplicated drawings. That's exactly what the geometrical optics is based on. So we want to use a simplified way of analyzing the direction of the propagation of the light and phenomena such as reflection and refraction. You can see a few pictures here. On the right hand side, you can see a point source that's radiating the light energy in all possible directions, represented by these outward arrows that represent the light rays. And then here on the right hand side, you have a prism, and you can see the light ray as it is moving through the prism, and you can see how the direction of the light ray is changing. That's one of the basic phenomena related to the light. We know that light propagates along the straight lines as long as it propagates within the same medium. And if the light ray is changing its propagation from one medium into the other, then it is going to change its direction. That's so-called phenomenon of refraction that we already analyzed in the introduction to photonics. So that phenomenon can be seen here, and it's represented by the basic geometrical concept of a light ray who is changing its direction as it is propagating from air into the material that this prism is made out of. And again here at this point, when it is exiting the prism, it's changing the medium from the glass or material that this prism is being made out of to the air. And then finally on the bottom left hand side, you see here the curved mirror, and again an example of the light rays and how they are reflecting off of the curved mirror and focusing on one spot, that's so-called focal point. So these pictures here are a good representation of what we are going to be talking in this and the subsequent lectures, where we're going to be analyzing the propagation of the light through different components, optical components, by using a simple concept of a light ray that's based on geometry. So one more visual representation of the two phenomena that we're going to be focusing on in this lecture, one being a reflection of light and another one being a refraction or bending of the light. On the left hand side, you have a picture of reflection where you can see three parallel light rays that are here labeled as A, B, and C, reflecting off of the planar surface, creating the three reflected light rays following the law of reflection. And then here on the right hand side, you have a visual representation of the light bending or light refraction as the light passes from one medium into the other, specifically here from air into the glass and then back from glass to the air. So let's focus our attention to the first phenomenon, being a reflection of light. So let's see how geometrical optics approaches the phenomenon of reflection of light. So when the light is incident on an interface between the two transparent optical media, such as the surface between the air and the glass, or between the water and glass, four things are going to happen to the incident light. First, it's going to be partially or totally reflected. It is going to be scattered in random directions at the interface. It may also be partially transmitted via refraction at the interface and enter the second medium. And finally, it may also be partially absorbed in either medium. So what exactly are we talking about here? There is basically a few phenomena that we are mentioning here. The first one is being reflection. You can see here on the bottom left-hand side 4 parallel light rays being reflected off of the surface of the glass. Keep in mind that the phenomenon of reflection is not just happening from the mirrors, but anytime light hits the boundary between the two media, there is going to be the certain amount of reflection taking place, sometimes more, sometimes less. If you are dealing with a mirror with a silver surface in the back, then the reflection is going to be much more pronounced. However, if you have other media such as shiny objects like a metal surface or glass, you're also going to have a certain amount of reflection, partial reflection, that will basically enable you very often to see the contours of your body shape if you're in front of that type of object. So that's reflection. Now the scattering is basically kind of a similar phenomenon, but it's happening at a minuscule level where photons of light are basically reflecting off of the small objects that are on a scale of the wavelength of light. So for example, molecules of water or air would be in the order of scale of a size of the wavelength of a light. You can kind of compare that to the reflection of the small balls in a ping pong or billiard, where you're having the balls that's hitting another ball. So in this case, we have the balls of photons hitting the balls of molecules of air and then reflecting in many different directions. So the whole model of that type of a reflection is much more complex than the model of reflection of the larger scale type of objects such as mirrors, etc. And being much more complex, it requires a much more complex types of mathematical models to be analyzed. So that type of reflection is known as scattering. So there's different mathematical and statistical models that are being used to describe the phenomena of scattering of the light from small objects in random directions. And then there's also transmission, meaning the light is entering the second medium. In this case here, we have light coming from the air, and it's gonna be entering the glass, and that's so-called transmission. That's also related to the concept of a bending of light or refraction. And finally, the light is gonna get absorbed in each medium. So that's another way of light interacting with the medium, where the intensity of light is being reduced. In other words, the energy of light is being transferred to the atoms and molecules of the medium through which the light is propagating. Those types of phenomena are not going to be analyzed in geometrical optics, but they are important to be mentioned here because they are directly related to how the light interacts with the medium, including the light reflection and the bending of light that we are going to be focusing on in this class. Now that we mentioned different types of phenomena that are taking place at the boundary of the two media that describe interaction of the light with the medium, we also want to establish a few assumptions that would have to be applied in order to apply the concepts of geometrical optics. As already mentioned, for example, absorption of light is not going to be analyzed in geometrical optics. So we want to see what would be the boundary conditions that we need to apply in order to be able to implement the concepts of geometry in the subfield of geometrical optics. So number one, we are going to consider only smooth surfaces that give rise to so-called specular reflections. You can see on the bottom the two visual representations of two different types of reflection, one being the specular reflection, another one being a diffuse. In the case of a specular reflection, you have a very smooth surface of glass. So the reflection is basically creating reflected light rays that are parallel to each other, while in the case of a diffuse reflection, we are dealing with a more of a rough surface. So although the incident light rays were parallel, reflected light rays are not parallel anymore. They are basically diffused in many different directions. So those types of phenomena are not going to be analyzed in the geometrical optics. So geometrical optics, as a first assumption, places is the smooth surfaces that give rise to specular, regular, or geometric reflections. Number one, we are going to ignore rough, ragged, uneven surfaces that give rise to diffuse or irregular reflections. And finally, as the third assumption, we are going to ignore the absorption of the light energy. In geometrical optics, we are not focusing on the intensity of light. We are just focusing on the directions at which light propagates. So that's an important distinction between the geometrical optics and the other fields of photonics. So in geometrical optics, we are not focusing on the intensity of light. We are not focusing on the energy of light. We are not focusing on the particle behavior of light or photons, but rather focusing on the directions of propagation of light, how the light changes its direction, how it's reflecting, how is it bending, etc. So absorption as a phenomenon where the light energy is being transferred to the medium while the energy of light is being reduced is not to be considered in the field of geometrical optics. So once more, we are ignoring the absorption of light energy that most always occurs along a path of a travel. Keep in mind that the absorption is an important consideration when the amount of light energy transmitted from source to receiver is a factor of concern. As for instance, when we see as much energy as possible to pass through an optical system such as microscope. Those types of concerns are not to be considered in geometrical optics, which is the topic that we are discussing here. On this slide, we are elaborating on the law of reflection. So we said that we are analyzing two phenomena in geometrical optics, one being a reflection or bouncing of light, another one being refraction or bending of the light. The first phenomenon of reflection, is described by so-called the law of reflection. So the law of reflection are basically telling us in what direction is light going to get reflected off of a specific surface. And that law of reflection states that the angle B, in our case, which is a reflected angle, is equal to the incident angle A. So what do we mean by the incident angle and what do we mean by the reflected angle? So if you focus your attention to the picture on the left-hand side, what we have here is on the bottom in a horizontal plane is a reflecting surface, and then we have an incident light ray. So that's the originating light. So incident light is, as you can see, moving along this path, along this direction, and then this point here is hitting the reflecting surface. That's so-called point of reflection. Now, the light is going to get reflected along a specific direction that's represented here by this reflected light ray. The question is, what is that direction? How can we determine the direction of the reflected light ray? So the law of reflections comes into play here. So the way how we can establish that direction is basically you establish first the plane in which these two light rays are positioned. So you can see here this vertical surface. So you basically establish the vertical surface, vertical plane in which the two light rays, the incident light ray and the reflected light ray, are sitting. And then also you're creating this so-called normal reference axis that's perpendicular to the reflecting surface. So as you can see here, we slowly are introducing geometrical concepts. So if you're not fully familiar with the geometrical concepts such as angles, it's very important to review those concepts. So the first concept that we're introducing here is the concept of the perpendicular or right angle equal to 90 degrees. So this reference line or normal is perpendicular on the reflecting surface at the point of reflection. And then you can see here two angles. The first angle is angle that the incident light ray is making with a reference line. That's our angle A. And then over on the other side, we have the angle that reflected light ray is making with a reference line. That's our angle B. According to the law of reflection, the incident angle A and the reflected angle B are equal to each other. And that's how we can establish the direction at which the reflected light ray propagates. So once you measure the incident angle A, over on the other side you can establish that same angle, or you can establish a reflected angle that is going to be equal to the incident light angle that is going to determine or define direction at which the reflected light ray propagates. So once more, we are establishing two angles relative to the reference line, reference axis that's perpendicular to the reflecting surface. The two angles that are being made by incident and the reflected light ray relative to the axis are equal to each other. And then also it's important to mention that incident light ray, the the reflected light ray and then reference line are all positioned in the same plane. In this case, you can see this vertical plane that's represented in this picture. You can use this concept of the light of reflection to establish, for example, the picture or mirror image of yourself on the mirror. So here you can have a real face, which is yourself, and then here in the back you can see your mirror image that is created by using the concept of geometry and light rays. As you can see here, we have a few light rays that we analyzed here to establish the mirror image. The law of reflection is to be applied not only to the planar reflecting surfaces, but also to any other smooth surface. So as we already mentioned, the assumption is that the surface is smooth, but it does not have to be planar, doesn't have to be on the plane. It can also be curved. So here we have an example of the reflection off of the curved surface. So talking about some sort of curved mirror here, and you can see here the incident ray coming from the from the left side in a horizontal direction, hitting the curved mirror at the point P. That's our reflecting point, and you can see here reflected light ray. So we are using exactly the same concept as presented on the previous slide. So we would first establish the reference line or reference normal that's perpendicular to the point P. Now here you have to be a little bit careful because we are dealing with a curved surface. So what would you want to create first is this straight line here. You can see this short straight line here that's touching the surface of the mirror only at one point. That's so-called tangent. And so once you create this tangent line that's touching the mirror only at one point, then you create this perpendicular line or reference line that's going to be perpendicular to this so-called tangent. So again, tangent is a small plane segment of surface tangent where reflection takes place. Once you created a reference line, then you apply the concept in exactly the same way as on the previous slide in the case of the plane surface, where you are looking at the incident light ray, establishing the incident angle A, and then over on the other side would construct the same angle of the same identical to the incident angle A to establish the direction of the reflection of this specific light ray. Exactly the same concept, is just that in this case the mirror is of the curved nature, and in such a case you would have to establish the straight segment that's touching the mirror only at one point, so-called tangent, and then you proceed with the establishment of the reference line, construction of the incident angle, and finally reflected angle. So here's an example. What we have here is a curved, so-called concave curved mirror, and what you can see here are basically 4 light rays that are labeled here as A, B, C, and D, and you are asked here to apply the law of reflection and to create a complete so-called ray trace diagram of the 4 light rays. So by ray trace diagram we mean the establishment of the reflected light rays that would be the result of the reflection of the light rays A, B, C, and D off of this concave curved mirror. As you can see here, we have already established the points of reflection, the point P1 for the light ray A, the P2 for the light ray B, P3 for the light ray C, and finally P4 point of reflection of the light ray D. And the question is how we are going to establish the reflected light rays. So you're going to be using the concepts presented on the previous slide, where you're going to be establishing the tangent at the point P1, a tangent at the point P2, point P3, point P4, and then constructing the reference line perpendicular to the tangents, and then measuring the incident angles for each of the 4 light rays, and then over on the other side of the reference line establishing the reflected angles. All that is presented on this picture. So you can see, for example, for the light ray A, the reflecting point is the point P1. Here we established the tangent segment and then created the reference line, which is this dotted line that's perpendicular to the tangent. And then we measured this incident angle that the light ray A is making with the reference line. And then over on the other side of the reference line, we have established the reflected angle, and then also reflected light ray that we here labeled as A prime. Same concept is applied for the light ray B at the point P2, and then the light ray C at the point P3, and finally the light ray D at the point P4. You can see the specifics of the light ray D, since the light ray D is actually perpendicular to the tangent. The incident angle in this case is equal to the 0 degrees because your reference line is going to be constructed along the direction of the incident light ray. In other words, the incident light ray and the reference line are perfectly overlapping. In other words, your incident angle is equal to 0 degrees, which means that your reflected angle is also going to be equal to 0 degrees. In other words, the reflected light ray is moving along the same path but in the opposite direction. Let's now look at the second phenomenon important for the geometrical optics, and that is transmission or refraction of light at optical interfaces. So here we are not analyzing the bouncing of the light rays off of the surface of a specific medium, but rather light passing into the second medium. So in the picture on the right hand side, you can see the incident light ray, and then you can also see the reflected light ray, which we analyzed on the previous slides. However, now we are also looking at the third light ray, which is this refracted light ray that enters the second medium. So we are analyzing the two media here, the first being the air, and then the second being this medium that's labeled as refracting medium. It can be a glass or plastic or any other medium. And you can see that a certain amount of light is gonna enter the second medium in the form of a refracted light ray. So we would want to analyze the direction at which this refracted or light ray propagates to the second medium. So once more, when the light is incident at an interface between the two media, it's going to be partially reflected and partially transmitted. So the partially reflected light ray is analyzed through the phenomenon of reflection and the law of reflection, while the transmission into the second medium is going to be analyzed through the phenomenon of refraction or bending. We're also going to establish another important law, so-called the Snell's law of refraction, that is going to determine direction of the propagation of the reflected light ray. So incident light will be partially reflected according to the law of reflection and partially refracted into the second medium. The bending of light rays at an interface between the two optical media is called refraction or bending. What you can immediately observe here is that refracted light ray is not propagating along the same line as the incident light ray. You can see the incident light ray is moving along this line, and you can see how the direction of propagation is changing. It's not continuing along the same straight path. So that's what we mean by bending or refraction. So we want to kind of quantify in what direction the light ray is going to get bent or refracted as it enters the second medium. So that is going to be the topic of discussion in the next few slides. Before we analyze in a full detail the phenomenon of bending or refraction of light and how to quantify it, there's an important concept that has to be introduced that's going to play an important role in the analysis of the refraction of light, and that's so-called index of refraction. Index of refraction is an important parameter that defines the properties of a medium, optical properties of the medium. So if you have two media, let's say air and glass, and light is propagating from air and glass, the amount of light bending or light refraction is going to depend on the indices of refraction of air and glass. So the two transparent optical media that form an interface are distinguished from one another by so-called index of refraction, which is a constant that's generally labeled as n. And there's a little bit more of meaning of index of refraction. It turns out that the light is not only changing the direction as it is propagating from one medium into the other, but it's also changing its speed and its wavelength. So that's something that we're not going to be analyzing here, but just remember that light propagates at a constant speed that can change if the light is moving from one media into the other. And this so-called index of refraction is a parameter that defines that ratio of how much is the speed of light reduced in a specific medium relative to the speed of light in a vacuum. And that's basically the definition of the index of refraction. You can see this simple formula here. N being the index of refraction is equal to C over V, where C represents the speed of light in a free space or vacuum, and V is the speed of light in the medium under the consideration. So for example, if your index of refraction is equal to 1.5, that means that the speed of light in a free space, in a vacuum, is 1.5 times more than the speed of light in that specific medium. So that's the physical meaning of the index of refraction. So here on the right hand side you can see the table with different types of materials, starting with the air and going all the way to silicon, and each of these different substances or materials, they have an associated index of refraction. That's basically telling you again how much the speed of light is reduced in that medium. For example, if you're looking at the germanium, you can see that index of refraction of germanium is equal to 4.1, which means that the light is propagating through germanium 4.1 times slower than it propagates in a free space or in a vacuum. So we also say that a medium is optically more dense if it has a larger index of refraction. As already mentioned, the index of refraction is going to be playing an important role in the next phenomenon that we're going to be analyzing, and that's the refraction or bending of the light. Let's now look at the physical specifics of the light refraction or bending of the light. Now that we know a little bit about the index of refraction being an important parameter, we want to look at the two cases here. On the left hand side, you can see the two media separated by this boundary. So we have a medium that's above the surface, that's characterized by the index of refraction N1, and then also we have the medium below the boundary that's characterized by the index of refraction N2. What you can see here is that the index of refraction of the above medium is lower than the index of refraction of the below medium. In other words, the N1 is a smaller number than N2. We can also say that the below medium is optically more dense than the medium above the surface. Now, it turns out that when the light propagates from optically less dense medium into the optically more dense medium, again, optically less dense is the medium that has a lower index of refraction. So here we have optically less dense medium above the surface, and below the surface we have optically more dense medium. It turns out that light is going to bend so that refracted light ray is going to bend towards the reference line. You can see here that we established the reference line here similar to how we were been establishing the reference line in the case of a light reflection. So again, you have the surface between the two media, and then you are going to construct this line here that's perpendicular to that surface of the boundary surface between the two media. So that's this dotted line, and you can see that in this case, reflected light ray is kind of bent towards the axis, and that's the important property that can be observed when the light propagates from optically less dense into the optically more dense medium. So it's very important to remember, again, when the light propagates from optically less dense to optically more dense medium, it's going to bend towards the axis. The other case is the opposite case. So in this case here, you can see here that incident light rays is coming from the bottom up, from the medium below, that's right now having like higher, it's optically more dense. So now the medium from which the light originates is optically more dense than the medium into which the light is gonna be transmitted. So right now we're moving from optically more dense into optically less dense medium. It turns out that in this case, the light is gonna bend away from the axis. You can see this refracted light ray is bending away from this dotted reference line. So that's also important to remember. When we are moving from a optically more dense medium with a higher index of refraction to optically less dense medium with a lower index of refraction, the refracted light rays are going to bend away from the normal. This is extremely important because it is going to be at the core of the operation of the optical fibers. We are going to talk a little bit about optical fibers in this class, and much more in detail in course 3 of this series that is going to be where we're going to be analyzing the fiber optics concepts much more in detail. So again, remember, memorize these effects since they often help us trace the light through optical media in a generally correct manner. Okay, let's now quantify the phenomenon of bending of light or refraction of light. We are going to use the law that's known as the Snell's law of refraction. It's been named after a Dutch astronomer, Willebord Snell, who formulated this law back in the 17th century. Here we have to use a little bit of a trigonometry, so it would be very useful if you refresh your knowledge of trigonometry. If you don't have a knowledge of trigonometry, we're going to be just simply using a calculator to do any kind of calculations that will be necessary to solve some of the mathematical problems. So what we have here is we are relating so-called sines, which is an important function that can be applied on an angle. So we're going to be relating the sines of angles of incident and refraction at an interface between the two optical media. You can see the formula on the left-hand side. So we are going to explain this formula, that this formula is a mathematical expression of the Snell's law. So similar to the phenomenon of reflection, we're going to establish two angles here. First one being the incident angle that the incident light ray makes with the reference line. And then we also have a refracted angle, that's the angle that the refracted light ray is making with the reference line. Those two angles here are labeled as I and R respectively. So angle I is our incident angle and angle R is our refracted angle. In addition to the angles I and R, we also have two indices of refraction. The first being an Ni, which is the index of refraction of the medium from which the incident light ray is originating. That's our first medium. And then you also have N sub R, which is the index of refraction of the second medium into which the light is going to be refracted. And this formula connects a few of these parameters. You can see that you would want to multiply the index of refraction of the incident medium to the sine of the incident angle, and then make it equal to the product of the index of refraction of the second medium multiplied by the sine of the refracted angle. So that's basically the formula that is going to be applied, where we can, so if you have three variables known, you can calculate the fourth variable. Most of the time you're going to be calculating this refracted angle R, that's usually unknown. So you would know the indices of refraction of the incident and the refracted medium, which is going to be N sub I and N sub R. And you're also going to be, also the incident angle is going to be known to you, so you're going to also have I. So you're going to have Ni and I and then R as known values, and then you're going to be from this formula extracting and calculating the value of the refracted angle to establish direction at which the refracted light ray is going to propagate. So here's an example of how to apply the Snell's law of refraction explained on the previous slide. So here we are analyzing a handheld optical instrument that's used underwater. We have a light that's incident from water onto the plane surface of the flint glass at an angle of incidence of 45 degrees, and we would want to calculate what is the angle of reflected light off of the flint glass surface. Does the refracted light ray bend toward or away from the normal? And finally, in the third portion of this math problem, we would want to calculate what is the angle of refraction at the flint glass surface. Let's first create a sketch of our problem that we're trying to analyze. So here, this straight line is going to represent the boundary between the two media. As the problem explains, we are analyzing the light propagation from the water onto the glass. So this is going to be our boundary. And so above here we have a water. We know that the water has index of refraction equal to 1.33 from one of the previous slides where we presented the table with the different indices of refraction. And then down here we have a glass, And for glass, we're going to assume that the index of refraction of the flint glass is equal to 1.5. So here we are going to construct the point P, at which we are going to assume is going to be the point of reflection, where the reflection and refraction are going to take place. At that point, we are going to create a reference line that's going to be perpendicular to the surface boundary between the two media. So I'm going to use here my protractor to create this line that's perpendicular to the surface boundary. So I'm using the protractor. Here's my 90 degrees. And then I'm establishing this line here that's perpendicular to the surface boundary. So that's my reference line. And then also the problem indicates that the incident angle is equal to 45 degrees. So again, I'm going to use my protractor here to create a 45 degree angle that's going to represent the incident light ray. So here's my incident light ray. And this angle here, again, so this is incident light ray. This angle here is going to be angle theta 1. That's going to be our incident angle. So to answer the part A of the problem, we are asked to figure out the angle of reflected light. We know that according to the law of reflection, so law of reflection, the incident light angle theta 1 has to be equal to the reflected angle theta r. Since theta 1 is equal to 45 degrees, means that our reflected angle theta r is also going to be equal to 45 degrees according to the law of reflection. So that would answer the part A of this problem. If you want, you can use a sketch on the left hand side to further construct the ray tracing diagram, where you're going to be measuring angle of 45 degrees in the over on the other side of the reference line. That's going to represent the reflected light ray. So this is constructing this sketch is not required from required in this problem, but is always a good practice to try to provide a correct geometrical sketch, because sometimes you're going to be using the geometrical sketch to figure out a solution to a specific math problem. So this here is going to represent my reflected light ray. And then this angle here is my theta r. Now, moving on to the part B of the problem, you're being asked to determine whether the refracted or bent light ray bends toward or away from the normal. Now, the fact that N1 is lower than N2, N1 being 1.33 and then N2 being 1.5, indicates that we are moving from optically less dense medium into optically more dense medium. And we know that in such a case of refraction from optically less dense to the optically more dense medium, the light is gonna refract towards the axis. So the answer to the part A of the problem is light bends toward the axis. So we can assume that that direction is going to be like this. So this is going to be our refracted light ray. And as you can see here, it's bending towards the axis. In other words, this angle here, that's going to be our angle theta 2. That corresponds to the so-called refracted angle, is going to be lower, is going to be smaller than the incident angle theta 1. In the part C of the problem, you want to determine this angle of refraction that we labeled as theta 2. In order to do that, you're going to apply the Snell's law of refraction. So here is the Snell's law of refraction. So the index of refraction of the first medium times the incident angle, sine of the incident angle theta 1, according to the Snell's law of refraction, has to be equal to the index of refraction of the second medium times the sine of the refracted angle θ2. So what we're going to do here is we are going to substitute for known values. So for n1, we know that it's equal to 1.33. So 1.33 times sine of the incident angle θ1. That's also known. θ1 is equal to 45 degrees. So sine of 45 degrees would have to be equal to n2, which is equal to 1.5 times the sine of the angle θ2. So we can do this math here. We're going to use the calculator. So first we want to figure out this trigonometric function here. So we're going to enter 45 degrees sine and then multiply the sine of 45 degrees by 1.33 to come up with the value of 0.94. So on the left hand side of our equation we have 0.94 equal to 1.5 times sine θ2. And then from here, the sine of the θ2 is going to be equal to 0.94 over 1.5. So we're going to divide this by 1.5, come up with a value of 0.627. 0.627. So the sine of the refracted angle is equal to 0.627. We need a refracted angle, so from here we can extract the refracted angle θ2 by using an inverse sine. So sine inverse of 0.627. So we're going to use the inverse sine function on my calculator to come up with the angle of 38.8 degrees. 38.8 degrees. So that's my refracted angle. So if you look at my picture, my sketch, this angle θ2 is equal to 38.8 degrees, which is less than the incident angle that's equal to 45 degrees. In other words, the light bent towards the axis as we indicated in the part B of this problem. This concludes the example number 2, in which we apply the Snell's law of refraction on a specific example. The next important concept that we would want to briefly introduce is the concept of the critical angle and so-called total internal reflection. Here we are analyzing the bending of light still, and we are analyzing the propagation of the light from the optically more dense into the optically less dense medium. So as it's indicated on the picture on the bottom left-hand corner of this slide, we have the boundary between the two media, and you can see here a few light rays that are labeled here as 1, 2, 3, and 4. They are originating from the medium that's below the surface, characterized by the index of refraction Ni, and the light is basically gonna attempt to propagate into the second medium through the phenomenon of refraction. The second medium, which is the medium above the surface, is characterized by the index of refraction Nr, and you can see here that the index of refraction of the medium below the surface is larger than the index of refraction of the medium above the surface. In other words, the medium below, which is our originating medium, is optically more dense than the medium above the surface, which is optically less dense medium. We know from one of the previous slides, we explained that in the case of a light propagating from optically more dense to optically less dense medium, the light is gonna propagate or refract or bend away from the axis. And you can see that in the case of the light ray 2. You can see how that the light ray 2 hits the surface, boundary surface between the two media. At this point here, we have constructed this dotted line, which is our reference line, and you can see how this light ray here, as it enters the medium above the surface, it's bending away from the axis. Now, an interesting phenomenon is going to take place if we start changing the direction of the incident light ray. So you can see here in the case of a light ray 3, we have increased the incident angle. You can see how this incident angle here, that's labeled I2 in the case of a light ray 2, is increased in the case of a light ray 3. So larger the incident angle is, the light is going to bend away from the reference line more. And you can see here that in the case of 3, we have a very, very interesting case where light has bent away from the axis to the point where it does not enter the second medium at all. So in the case of a light ray 3, you can see again light bending, but right now it bent away from the axis so much that it does not enter the second medium at all. That's the case of so-called total internal reflection. So that don't be confused by using the term reflection, because this is a refractive phenomenon, right? So because here we are trying to analyze the case where the light is attempting to enter the second medium, but we are adjusting the incident angles of the light rays to the point where the light does not enter the second medium, and establishing a phenomenon that's known as a total internal reflection. So we are trying to kind of, by changing the direction of these incident light rays 1, 2, 3, and 4, we are trying to keep the light within the first medium, within the medium below the surface. The minimum angle at which the total internal reflection takes place, which is this angle here in the case of a light ray 3, is so-called critical angle. So that's again an incident angle at which the light wave is fully bent away to propagating along the surface boundary between the two media. In other words, there is no wave propagation into the second medium, and that's our light ray 3. If you continue increasing this critical angle, such as in the case of a light ray 4, you can see that not only that the incident light ray is gonna be moving along the boundary, but it's gonna actually get quasi-reflected into the first medium. So that's so-called total internal reflection. The boundary case for the total internal reflection is an incident angle known as a critical angle at which the total internal refraction occurs. We can actually calculate this critical angle for specific two media. So we can use the Snell's law of refraction that's shown here, where as our refracted angle we're going to be using the angle of 90 degrees. So that's the case of the light ray 3, right? So if you look at the light ray 3, right, so the refracted light ray 3 makes an angle of 90 degrees with the reference line. So our refracted angle is equal to 90 degrees. And so you're going to substitute for the refracted angle of 90 degrees, and then you also have two indices of refraction for the two media, the numbers n sub I and n sub r. So you basically know everything except for the incident angle, which is basically the case of a critical angle. So from this formula you can extract the critical angle IC and establish this formula that you can see here on the right hand side, where you can calculate a specific critical angle for the two media at which the total internal refraction is going to occur. We are going to be analyzing how to apply this formula in one of the mathematical problems on the slides that follow. The concept of the total internal reflection is actually extremely important for the case of optical fibers. Optical fibers represent glass-made optical cables through which we are establishing the propagation of the light. It's very frequently used these days in telecommunications, because if you're using the light, you are establishing almost unlimited bandwidth, which is extremely important for today's types of communication, where we are using all the real-time video streaming that requires a lot of bandwidth and a lot of capacity. So that's been supported by the optical cables, through which we are not sending the electrical but rather an optical signal. And the way how the light is contained within the optical cable is through this so-called phenomenon of total internal reflection that we explained in the previous few slides, and we're also showing on this slide. The optical cable is made out of so-called core, which is this inner cylinder, and then another layer of glass of different index of refraction. So what's basically happening, what you can see here is in a light blue is the core of the optical fiber, and then in gray is the outer layer. So these two parts of the optical fiber, one being the core and the gray layer being so-called cladding, they have different indices of refraction. The core has a higher index of refraction than the cladding, so when the light hits the boundary between the core and the cladding, since it's trying to propagate into the cladding, and cladding has a lower index of refraction, we are launching the light from specific directions that would enable total internal reflection, where the light is being contained within the core and keeps bouncing back and forth through the core, and that's how we are basically transferring the information from one side of the optical fiber into the other side of optical fiber. So that's kind of like a basic explanation of how optical fibers are working. As I already mentioned, there's a whole series of lectures titled Fiber Optics, where we are going in much greater detail explaining the fundamentals of total internal reflection and the way how the optical fibers are working, what are important specifics of the optical fiber, their dimensions, how they're being fabricated, and then also what are the difficulties that have to be overcome for the light to properly propagate and carry information from the source through the optical fiber all the way to the other side, to the receiver or recipient of the information. The phenomenon of a total internal reflection is not just used in optical fibers, but has found many other applications, one being also in the business of jewelry. So if you're looking at the diamond, the sparkly appearance of a diamond that makes it so expensive is actually due to the concept, due to the phenomenon of the total internal reflection. So the jewelers are basically shaping the diamond in shapes that would enable the total internal reflection that would create this sparkly appearance of those gemstones. So here's an example in which we are basically analyzing the phenomenon of total internal reflection used by the diamond cutters to shape the gemstone in such a way that the light incident on the entrance face is totally reflected back out the entrance face. You can see the picture here. Such a total internal reflection causes the diamonds to sparkle, and the question here is, what is the critical angle for light at the diamond air surface? Okay, to solve this problem, we are going to need a few pieces of information. The first one being the index of refraction of a diamond. If we refer back to the table presented on one of the previous slides, we will get the information that the index of refraction of a diamond is equal to 2.42. We also know the index of refraction of air equal to 1. And then in order to calculate the critical angle for the case of a diamond, we need the formula presented on the previous slide. So theta critical equal to inverse sine of the second medium, which in our case is air, over the index of refraction of the first medium, which in our case is a diamond. So it's just a matter of substituting for these two values and then doing the calculation. So inverse sine of index of air being 1 over index of diamond being 2.42. So if you use the calculator, 1 over 2.42 gives us the value of 0.413. So our critical angle is going to be equal to inverse sine of 0.413. And then you can calculate the inverse sine by hitting the second function, blue button, inverse sine. So we get for the critical angle 24.4 degrees. So critical angle in our case is equal to 24.4 degrees. So that's the angle at which the light should be shown onto the surface between the diamond and air in order to produce the total internal reflection that would make our diamond sparkle. In this example 4, we have another mathematical problem to be solved that is using the phenomenon of total internal reflection. We are here analyzing actually the optical fiber with a few important parameters to be used to figure out what is the critical angle. So you can see here that we are analyzing so-called step index fiber that's a 0.0025 inch in diameter, has a core index of 1.53 and a cladding index of 1.39. We would want to figure out what is the so-called maximum acceptance angle, as well as what is the critical angle that is going to be enable total internal reflection at the point R. So let's look at this mathematical problem together. Okay, so the first that we're going to calculate is the critical angle theta c that's referred on our sketch that you can see on this slide. So the critical angle theta c is going to be determined by the indices of refraction of the core and the cladding. So please refer to the point R at which the total internal reflection takes place. That's characterized by the angle theta C. So we're going to use the formula from the previous slides to determine this critical angle theta C first. So in this problem, we are given two indices of refraction: the index of refraction of the core, that's equal to 1.53, and then also the index of refraction of the cladding, that's equal to 1.39. Using the formula for the critical angle, we can figure out, we can determine the critical angle. So the critical angle theta C is equal to the inverse sine, the second medium, which in our case is a cladding, over the first medium, which in our case is a core. So from here we have inverse sine by substituting for these two indices of refraction. Here we have 1.39 over 1.53, which can be calculated using a calculator. So we have 1.39 over 1.53 gives us the value of 0.908, and then we are going to take inverse sine of 0.908 by pressing the blue button, and then this function here. So the critical angle is equal to 65. We're going to round to one significant digit, 65.3 degrees. Now the next step is to focus at the point P. At the point P, the light is coming from the air, from the outside, and entering the core. And you can see that at the point P, we also have the phenomenon of refraction. So at the point P, again, the light is being launched from the air, from the outside, into the core of the fiber. And as you can see, the direction from which the incident light ray is coming from the air and hitting the point P is not the same as the direction of the refracted light ray that is going to establish the refracted light angle theta R. So the first that we would want to calculate is the refracted angle theta R. So if you refer to the picture shown, the angle theta R is directly related to our previously calculated angle theta C. So the triangle that's made out of the vertices P and Q and R is a right angle triangle, and we know that the sum of the angles in a triangle is equal to 180 degrees. So in this triangle PQR, we have three angles: critical angle theta C, and then the refracted angle theta R, and finally right angle right at the vertex Q, that's equal to 90 degrees. So the angle theta C plus theta R plus the right angle 90 degrees would have to be equal to 180 degrees, because we know that in any triangle the sum of the three internal angles is equal to 180 degrees. Now here we have all the information except for the angle theta R. We know that our critical angle from the previous calculation is 65.3 degrees plus theta R plus 90 degrees. So from this equal to 180 degrees. So from this equation, you can calculate the angle theta 3. So your angle theta 3 is going to be equal to 90 minus 65.3. So our angle theta R is equal to 24.7 degrees. Okay, now going back to our sketch, again, we want to focus our attention to the point P. You can see the point P, we have a phenomenon of refraction where the incident light ray is being launched from the air and it's entering the core. And what we want to calculate here is this angle theta M. That's our so-called minimum acceptance angle theta M. You can see that that's what's being asked in this problem. So we want to figure out this cone that angle theta M makes. So as long as we are within that cone defined by the angle theta M, all the light that's being launched into the core is going to be characterized by the total internal reflection. So what is that angle theta M? The way how we are going to determine angle theta m is we are going to apply the Snell's law of refraction at the point P. So we have an incident light ray from the air hitting the point P and then entering the core. So the Snell's law of refraction at that point is going to be equal to the index of refraction of air times the incident angle, which in our case is going to be our minimum acceptance angle theta m, is equal. Now what we have in the core, we have the refracted angle theta r, and we have also index of refraction of the core, which is 1.53. So our index of refraction over on the other side in the core is nc times the angle of the theta r. Now let's see what we have here. So again, n1 is the index of refraction of the air. That's our originating medium. That's equal to 1 times sine of unknown minimum acceptance angle theta m is equal to the index of refraction of the core, which is 1.53, times sine of the refracted angle. Refracted angle theta r is what we calculated in the previous step, equal to 24.7 degrees. So our sine of unknown angle theta m is going to be equal. Here again, we are going to use the calculator. So we're going to calculate the sine of 24.7 and then multiply that sine with 1.53 to get the value of 0.639. And then from here we can extract our minimum acceptance angle theta m as the inverse sine of 0.639, and then again use the calculator to apply the inverse sine. So inverse sine again we are going to apply by pressing the blue button for the second function and then hitting the sine button, and we're going to get the angle of 39.7 degrees. 39.7 degrees. So that's so-called minimum acceptance angle. As you again look at the sketch, you can see that that minimum acceptance angle of 39.5 degrees is basically defining all possible directions from which we should shoot the light into the core to ensure the total internal reflections to take place. So as long as your launching angle is smaller than 39.7 degrees, your light is gonna enter the core and then it's gonna continue bouncing through the total internal reflection along the core, and that's going to enable transmission of the light and transmission of the information through the optical fiber. Next interesting phenomenon that we would want to look at that's directly related to the refraction or bending of the light is so-called the retroreflection. It's an important term that you would want to be familiar with as a photonics technician, because as I said, it's very, very often used in the case of optical components known as prisms. So the glass prisms are often used to bend light in a specific given direction, as well as to bend it back again. So when a light enters the prism at one phase, it is going to exit at another, and that exiting rate is going to deviate from its original direction. What do we mean by this? So let's look at the prism. You can see here the prism, right? So the base of this prism is a triangle. So imagine a three-dimensional object whose base is of a triangular shape. And you can see here the light ray coming from the left-hand side, hitting this point here, and then it's gonna enter the prism. The fact that the prism is made out of different material than the surrounding air is gonna result in a bending of the light. So you can see how the light ray changed its direction. And then again at this second point of refraction, when the light is exiting the prism, moving back into the air, we also have the bending of light or light refraction. Now you can see here two distinct paths of the light as it propagates to the prism. First one being the direction of the incident light, and then we have the light ray that's moving through the prism in a specific direction, and then finally the light that's moving along a specific direction after it exited the prism. Each of these three paths of the light are not in the same direction due to the phenomenon of light refraction. So what we are saying here is that if you're comparing the light ray before the entered the prism and the light ray after it exited the prism, those two directions are not the same. In other words, the light ray here has deviated from the direction of this light ray after it exited the prism has deviated from the direction of the incident light ray. So if you take this incident light ray and you extend the line along it propagated, and you establish that line, and then you measure the angle between that dotted imaginary line that represented the direction of the incident light ray, and measure the angle between that imaginary line and the direction of the deviated light ray, we are establishing this angle here, that so-called angle of deviation. We're using the Greek letter delta that you can see here. So that's so-called angle of deviation. That's basically telling us how much the light ray, after it exited the prism, has deviated from the original light ray that entered the prism. We also want to introduce a few other terms here. The first one being isosceles prism. So we're talking about a prism whose equal or that has equal base angles. So you can see here we are talking about a triangular prism, or prism that has a triangle as its base, and triangle is a geometrical shape that is described by these three internal angles. So two out of these three angles in the case of isosceles prism are equal to each other. So these two angles here, you can see them down on the bottom, this one and that one there, they are equal to each other. Those are so-called base angles. The third angle does not have to be equal to the other two. So we just have to have 2 out of 3 angles equal to each other, and that's the condition for the prism to be considered so-called isosceles prism. So that's one thing. Another thing is so-called apex angle. Apex angle is the third angle. So that's this angle here. In our case is equal to 30 degrees. And then also, of course, we have the index of refraction of the material that the prism is made out of. So what we want to do here is we want to analyze a very, very interesting phenomenon that is taking place here. What you can see here, I mean, we'll have a lab experiment in which you're going to be actually analyzing this in the lab. So here we're going to just explain the concept and then practice it in the lab. So if you, let's say, have this type of a prism, and let's say you have a laser beam, you have a laser and you're shining the laser beam onto this prism, you're gonna have this light ray coming out. So if you put the back screen here on the right hand side, you're gonna see the red dot if you're using red laser. Now what you would also observe in the lab is that if you are changing the direction, if let's say you're holding this laser here that's shining this laser beam, light beam here, if you're changing the direction, meaning you are changing the direction of this incident light ray, it's kind of logical to conclude that the direction of this refracted light ray that's exiting the prism is also going to change. So if you're changing the direction of the incident light ray, the light ray that exited light prism is also going to change. So if both of these directions are changing, obviously the angle of deviation is also going to change, because the dotted line that represents imaginary line of a direction of the incident light beam is going to change. Why? Because we are changing the direction at which we are pointing the light onto the prism. And then also due to the whole refraction, the direction of this third light ray is also going to change. So it's going to affect this angle of deviation. Now, it turns out that if you are moving the incident light ray in a specific direction, so you can move it either towards this axis, so you are basically changing this direction to, let's say, direction like that, what's going to happen is that also this angle is going to change. So it turns out that for a specific direction of the incident light ray, you can find the smallest possible angle of deviation, so-called minimum angle of deviation. So once more, I'm going to repeat. For a specific direction, as you are changing the direction from which you are pointing the laser beam onto the prism, you can find a specific direction at which this angle delta, this angle of deviation, is going to be the smallest possible. So that's so-called minimum angle of deviation. And you can see how it's being represented, how that concept is being represented here on this plot, on this graph on the right hand side. Down on the bottom on the horizontal axis you have different angles of incidence, starting from 0 degrees and stretching all the way to 80 or 90 degrees. So that's basically this angle theta here. That's the angle at which you're pointing your laser beam onto the prism relative to this reference line. So if this angle is getting reduced, right, so you're kind of moving this laser beam more kind of perpendicular onto the surface, then you're basically looking at a specific angle along this horizontal line that's smaller. If you're increasing this angle theta, then you're kind of moving more towards the right on the horizontal axis of this plot. And you can see that for any angle, any incident angle at which you're pointing your laser beam onto the prism, you have a specific angle on a vertical axis that represents the angle of deviation. So for example, if you're pointing your laser beam at an angle of 40 degrees, right? So if this angle here is 40 degrees, then you will go up, you're going to find this point here, move in the horizontal direction, you're going to find about probably 16, 17 degrees. So this angle delta would be about 16, 17 degrees for a specific angle of incidence of 40 degrees. Now, you can also see the dip on this curve. And that dip, you know, is this point here at which your deviation angle is the smallest. So that's what we're interested in here. So we want to find the incident angle at which the angle delta is going to be the smallest, and that's exactly this point here. So at that point here, you have the lowest deviation angle that occurs when your incident angle from which you are pointing the laser beam is about, this is kind of like 27 degrees in this specific example. So it turns out that this concept can actually be used to determine the index of refraction of the medium that the prism is made out of, and that's what we're going to explain on the next slide. So on this slide here, you can see on the left-hand side of the slide is a rather complex formula that uses two signs and a few other parameters. On the left-hand side of this equation, you can see the index of refraction, and that's the index of refraction of the prism. So if you properly calculate these angles and you figure out this minimum deviation angle, you can use this formula to figure out the index of refraction of the prism. So that's actually going to be the experiment that you're going to perform in the lab. So you'll be given this type of isosceles prism. You're going to be given a laser pointer, so you're going to be shining the light on the laser prism until you figure out the minimum angle of deviation. You're going to record that minimal angle of deviation, which is going to be this angle delta subscript m. And then also we know the apex angle is going to be given to you. In this case, it's equal to 30 degrees. So you're going to substitute for the apex angle A for the minimum deviation angle delta. And then you're going to apply this formula to calculate the index of refraction of the material out of this prism is made. So to conclude, each prism shape of refractive index has its own unique minimum angle of deviation described by the formula. The refractive index of a transparent material can be determined by shaping the prism in the form of an isosceles prism and then measuring its minimum angle of deviation. That's what we're going to be doing in the lab. So we are not going to be shaping the prism in a specific form, but you're going to be given the prism. However, you're going to be performing all the measurements to determine through the measurement the minimum angle of deviation, and then applying this formula to figure out the index of refraction of the material that our isosceles prism is going to be made out of. So here's the numerical or mathematical problem that sheds more light into the whole concept of retro refraction and the minimum angle of deviation. So here, we have a specific scenario where you are working for a photonics company. Your supervisor hands you a piece of a transparent optical material of unknown index of refraction and asks you to determine that refractive index. So it's a medium, it's material, maybe something like a glass or plastic. And the question is, okay, how are you going to figure out the index of refraction? You are not given any kind of data sheet or, and not know any information about that medium. So what you can do is you would take that sample to your glass shop in a company. You would have it shaped in the form of an isosceles prism with an apex angle of 25 degrees in this case. And then, once you get that isosceles prism with the apex angle of 25 degrees, you're going to go back to your photonics laboratory, and you're going to use the laser beam and the prism table to figure out the minimum angle of deviation for this prism. And it turns out that minimum angle of deviation is 15.8 degrees. And here's the question for you. How would you figure out the index of refraction of this material based on the information given in this numerical problem, which is a representation of a specific case of you working in a photonics laboratory and figuring out index of refraction of an unknown material. So as indicated in the setup of this problem, we are given two pieces of information here. The first one is apex angle, capital A, being equal to 25 degrees. And then we also measure the minimum angle of deviation to be 15.8 degrees. So our delta sub m is equal to 15.8 degrees. According to the formula given on the previous slide, the index of refraction is equal to the sine of A plus delta m over 2 divided by the sine of the apex angle divided by 2. So we are going to substitute for the two angles. So we have a sine of 25 degrees plus 15.8 degrees over 2, and then all divided in a fraction by sine of 25 degrees over 2. So if we do a few of these arithmetic operations, we can figure out that the sine above the fraction line is to be calculated to be 25 plus 15.8 over 2 equal to 20.4. So sine of 20.4 degrees. And then below the fractional line we have sine of 25 degrees over 2, which is equal to sine of 12.5 degrees. So we are gonna again use our calculator to calculate these two trigonometric functions. So we have sine of 24.4 degrees equal to 0.349 divided by sine of 12.5 degrees, which is equal to 0.216. So if we divide these two numbers, so we're going to divide 0.349 by 0.216, we get a number 1.616 for the index of refraction of the material that this prism is made out of. You can also do a quick reality check. You can see that index of refraction here is larger than 1, which is what's expected. So index of refraction is always larger than 1. The lowest possible index of refraction is equal to 1 for the free space or vacuum. Next concept that we briefly want to introduce that's directly related to the refraction or bending of light is so-called the dispersion of light. What you see here on the right hand side is probably something that you came across, and this is a very popular and familiar picture where we can create a rainbow of colors by shooting the white light onto the prism. So there's a few important notes to be mentioned here. Number one, we know that the white light is made out of all colors. So if you combine all the colors in the rainbow, you create a white light. And what you have here is actually one of the first experiments that have been performed by the Sir Isaac Newton to confirm or to prove that the white light consists of all the colors. So he was actually playing with the prisms. He was actually making some of the prisms and then playing with the white light and realizing this important, interesting phenomenon of light that's known as a dispersion. So the question is how we can explain phenomenon of dispersion. How can we explain why would the white light break down into all these different colors that's being passed to the optical prism? It turns out that the index of refraction, as introduced previously, we said that that index of refraction is a constant number. However, that is not really entirely true. It turns out that index of refraction is actually changing with the wavelength of light. We also know that the wavelength of light is directly related to the color of light. So if you have a red light versus a blue light, the wavelength of light is going to be different. So for example, for the red color, we are talking about the wavelengths in a range of about 700 nanometers, while over on the other side of the spectrum you would have a blue and violet that are going down to as low as 400 nanometers. So it turns out that the index of refraction of the medium is changing with the wavelength of light. In other words, index of refraction for, let's say, a glass that's a prism made out of, index of refraction of glass is going to be different for violet light versus red light versus green light or yellow light. And you can see that on this graph on the left hand side. So let's pick, let's say, light flint type of material, and you can see here how the index of refraction is changing. It's not like a straight horizontal line. On a horizontal axis, you have different wavelengths starting from 400 nanometers going all the way to 700 nanometers, basically covering the entire visible spectrum of light from violet all the way to red. So for each of these different wavelengths, you can see that you have a specific point along a line that represents specific medium. And you can see that each of these points, if you project them onto the vertical axis, are going to be producing different numbers. So for example, if you go all the way down to 400 nanometers, which is a violet light, you can see the light flint is going to be having index of refraction of about 1.6. If you go over to the other side and you're looking at 700 nanometers, which is the red light, the light flint, if you take this point here and project onto the vertical axis, you can see that the index of refraction is not going to be 1.6 anymore, but significantly lower. So that's basically what this graph represents. So it represents, it quantifies different indices of refraction for different wavelengths for the same material. Now, why is this important for us? Well, we know that index of refraction is affecting how much light is bent. If you go back to one of the previous slides where we explained the Snell's law of refraction, we know that in the Snell's law of refraction, the formula that we analyzed, the amount of refractive angle, the size of the refractive angle is going to be directly related to the indices of refraction of the first and the second medium. So now that we have media having different indices of refraction for different colors, that means that different colors are going to be bent at different angles. And that's exactly what we're observing here. So the light is not gonna, the violet light is gonna bend at a different angle as a red light. So in other words, when we have all this white light here that consists of all the colors, when that light is moving, from air to the glass that prism is made out of, the different colors of the white light are gonna be bent at different angles, so they are going to be separated into this beautiful rainbow of different colors, and that's known as a phenomenon of dispersion. The phenomenon of dispersion has found its application in photonics. Specifically, very often we are using the prism-based components to create so-called spectrometers or spectroscopes that are being used to analyze different wavelengths of the light. We have a few of those simple spectroscopes in the lab. You may use them in the course 1, Introduction to Photonics, where we analyze the spectra of different types of white light. We looked at the incandescent light, at the fluorescent light, etc. And we analyzed what colors are present in a specific white light of a specific light source. So that's where the concept of dispersion of light has been applied. All these theoretical concepts that we introduced in this class, specifically reflection of light and refraction of light, have found many useful applications. Many different types of optical components are created to use the phenomena that we analyzed in this lecture. Specifically, prisms are very often shaped in different types of shapes that would be used to manipulate the light by changing its direction through the phenomenon of reflection and refraction. So you can see here a few different types of prisms. On the bottom left hand corner of the picture we have a right angle prism, and then we have a few other special types of prisms such as dove prism, pentaprism, and finally poro prism. So all these different types of prisms are being used again in a specific type of optical system to manipulate the light and to serve a specific purpose. So very often they are being used in binoculars, microscopes, telescopes, etc., where we're manipulating the light to serve a specific purpose. In addition to the prisms, we're also using the mirrors that rely on the concept of reflection. Those are also used in the different types of optical systems. Very often they are capable of high reflectivity, and as I said, they are being used in various optical systems. Here's an example at the end of the lecture, so-called poro prism that's being used in binoculars. So you have a few different pictures of binoculars here, including the internal look of the binoculars. So the poro prism basically consists of two right-angle prisms that you can see here. It's used in binoculars, produces so-called erect final images, and at the same time permits the distance between the object viewing lenses to be greater than the normal viewer's eye-to-eye distance. What is accomplished by that, we are able to enhance the stereoscopic effect produced by the ordinary binocular vision. So we are not going to be analyzing in detail how the binoculars work, other than showing you a few of these pictures, but I'm fully confident that if you fully understand the concepts of this lecture and you know how we can trace the light ray through different types of optical components, you would be able to analyze these types of simple systems. So in the subsequent lectures, we're going to be talking about manipulation, or how to trace the light through the lenses, how to trace the light through the prisms, how to analyze the light that's being reflected from the curved mirrors, and that's going to give you enough knowledge and a reasonable set of skills to analyze geometrically some of these simpler optical systems, such as binoculars or microscope or a telescope. So in this first lecture in the series of geometrical optics lectures, we introduced the subfield of geometrical optics. We defined the concept of the light ray and the wavefront that's at the core of ray tracing analysis based on geometrical optics. And then we reviewed the two important phenomena that would affect the direction of the propagation of light: phenomenon of reflection or bouncing of light, and then phenomenon of refraction or bending of the light. So these two phenomena are at the core of many different optical systems, such as telescopes and microscopes and the binoculars, where light is being manipulated in a specific way using geometrical concepts to serve specific application. With this, we are going to conclude our first lecture in a series of geometrical optics lectures. I hope you enjoy this lecture, and I'm going to see you next time.